Alright class, this is your notes on 6.4, sampling distributions and estimators. So what we're dealing with here in 6.4 is something called a sampling distribution of a statistic. So what this is basically saying is this is all the possible values a statistic can take on. A statistic means something like a sample mean, sample proportion, something that you get from a sample is what we refer to as a statistic. So we pick a sample size, so some sample size n, and it's every single possible value the statistic can take on, and it's the distribution, the likelihood that it takes on that value. Alright, so to give you an example, this is going to be something we kind of work through this whole entire section of notes. So consider we're going to repeat the process of rolling a six-sided die. We're going to roll it 5 times, and we're going to find the average roll, right? X bar, and then we're going to find the proportion of odd numbers of the results, like a proportion of the 5 numbers that we roll that are odd. Alright, and we're also going to find the population standard deviation for the probability distribution that we can come up with. Okay, so we're going to find the average roll for each roll of the die, alright, and then we're going to find the proportion of odd rolls that we get. Alright, and this is theoretical probability that we're talking about here when we're talking about the proportion. Alright, so expected value, that's the average roll. That's what this first part's saying. Find the mean roll. So remember, based on a probability distribution, you come up with all the different possible outcomes of rolling a six-sided die. I could roll a 1, a 2, 3, 4, 5, or 6, and each the probability of each one of these outcomes has a 1/6 chance of happening. So according to what we talked about back in chapter 5, the mean of this distribution is equal to the sum of the values, the x's, times the probabilities. So the values, these are the x's, 1 times a sixth plus 2 times a sixth plus 3 times a sixth, on and on and on, until we get to 6 times a sixth. Right, and then notice all of these are being multiplied by the same number, that 1/6. So I pull that 1/6 out front. Okay, that's just factoring. Pull that 1/6 out front, and I just have 1 plus 2 plus 3 plus 4 plus 5 plus 6, which adds to 21. And then 1/6 times 21 is 7/2, or 3.5. So the mean of this distribution is 3.5. That means if I'm going to roll a six-sided die, the expected roll is a 3.5. Alright. The expected long-run average, I guess I should say, is 3.5. If we keep rolling this over and over and over, we should expect an average of 3.5 on each roll. Alright, now find the expected proportion of odd rolls of the 5 rolls of the die. So we're rolling it 5 times. Okay, the probability any one roll is odd is a half. Okay, there's a 1, a 3, and a 5, and that's the odds, and then there's 6 total, so 3 out of 6 is a half. So the expected number of odd rolls, if I'm rolling 5 times, that's n. P is 0.5, so 5 times 0.5 is 2.5. So we expect 2.5 odd rolls for every 5 times we rolled, and of course if you find the proportion that's odd, that's 2.5 divided by the 5, so that's a half. Okay, so we would expect, since it's a half for every one, we would expect half of the rolls, half of the 5 rolls in a long big number of trials, we would expect half of them to be odd, half of them to be even. Alright, and then find the population standard deviation. So this is the formula for the population standard deviation of a discrete random variable. So the sum of, I'm adding up the values minus the mean. We found the mean to be 3.5 squared times the probabilities. So there's the value minus the mean squared for 1, 2, 3, all the way down to 6. Right, and then the probabilities is 6. I'm multiplying everything by 6. Same thing as before, I pull that 1/6 out, and that just means I'm adding up these deviations right here. 1 minus 3.5 squared, plus 2 minus 3.5 squared, all the way up to 6 minus 3.5 squared. I did that in my calculator. See this ANS answer? That means I'd been adding these pieces all the way up until I got to the 6 minus 3.5 squared. So this is what I got in the brackets, 17.5, and then I multiply that by the 1/6 on the outside. Right, that gave me this. That's everything underneath the radical. So the last thing I need to do is take the square root. So there's what I get when I go with the formula. But just remember, we had a shortcut method to do this with your calculator. List 1, put your x's that we did here. List 2, put your probabilities. 1/6 as a fraction is 0.16 repeating. And then remember, you do one var stats, L1 comma L2, and that'll give you the same mean. There's our mean of 3.5 that we got before, and then there's our population standard deviation. Okay, so you can get it that way. That's the way I would expect you to do it, but just reminding you that formula does give us the same thing. Alright, now let me talk about what it is we're doing. These are population values. This is the population standard deviation. This is the population proportion of odd. Right, this is the population mean of all of these trials. Again, the theoretical mean. Now, in practice, if I rolled a die 5 times, this is a possible outcome I could get. I could get 4, 3, 5, 1, and 3. Okay, if I got 4, 3, 5, 1, and 3 as my sample, that's one possible series of 5 rolls. I could compute that sample mean. 4 plus 3 plus 5 plus 1 plus 3, enter, divided by 5, and I get 3.2. Right, that's obviously not equal to 3.5. It's close, but it's not exactly there. And then if I come up with the other, alright, add those up, divide by 5, I get a mean of 4. Alright, so what I'm just showing you here is when I sample, there's variation in the sample that I get. Depending on what my sample is, my sample mean is going to change every time. We expect it to be somewhere close to 3.5. That's the expected value. It's the population mean. But when we sample, when we take sample means, we're not guaranteed to get that number. Okay, so the sample mean can vary. It changes. It's like a variable, just like we've been studying in chapter 5 and now a little bit in chapter 6. It's something that can change over time, depending on what sample you get. Well, that's the sampling distribution of the mean, the sample mean. So it's the distribution of all samples having the same sample size taken from the same population. Every single possible sample mean we can get from this scenario. Alright, we could get, all 1s, all 2s, all 3s, all the way up to all 6s. And then like we could get 1, 2, 3, 4, 5, 3, 4, 6, 2, 1. We could get any combination of 5 rolls, 5 numbers between 1 and 6, and we could have all these different means computed from that. That's what we're talking about here when we say the sampling distribution of the sample mean. Every single possible outcome that can happen. Now, if we do this a large number of times, over and over and over again, what this histogram represents is every possible sample mean. If you can read right here, it says sample means. So if I take 5 rolls, if I roll the die 5 times, yeah, I could get something down here way below 1.6. So I could get something down here like 1, meaning I get all 1s for all 5 rolls, but that's going to be very rare. It's not going to happen very frequency. So that frequency is low. Or I could get all 6s, but again, that's way up here. That frequency is low. What's most likely to happen is some, if I get a 1 or a 2, I'm also going to get, a 4 or a 5. It's going to kind of offset each other and bring me back to the middle as far as the average goes. So what we see, if we do this 10,000 times, 10,000 trials, what we start to see emerge is a bell curve. We see a bell curve start to form for the distribution of the sample means. So what we're going to see is the distribution of the sample means is approximately normal, and there's going to be a magic number we'll find out about in 6.5 that lets us know what our sample size needs to be to kind of guarantee we have this bell-shaped curve, right? Even if we didn't start with a normal distribution. Right, we really didn't here. We started with a uniform distribution. You know, everything was a probability of 1/6. Now we're having a bell-shaped curve, and notice what's in the middle of that bell-shaped curve. The mean of the population. Alright, so one important thing from this is notation. This means the mean of the sample means. Right, the mean of the sample means is equal to the mean of the population. Okay, so we get this bell curve. Remember, the center of a bell curve is the mean. Well, what's in the center of these sample means? The mean of the population. Alright, now let's keep going. Find the proportion of these that are odd. Right, remember, in theory, the proportion is supposed to be 50%, 50-50. Well, because I have an odd number, I really can't get 50-50, but we can still find the sample proportion. So the sample proportion, we use a P with a hat on it to represent sample proportion. So there are 1, 2, 3, 4 odd numbers out of the 5. So that's 4/5, which as a decimal is 0.8, 8/10. Okay, and then down here I have 1, 2, 3 evens and only 2 odds. So in this case, that's 2 out of 5. 2 out of 5 is equal to 0.4. So again, what I'm trying to illustrate with these samples is sometimes our values, our sample proportions, our statistics are bigger than the expected value or the population value. Sometimes they're smaller. Okay, but they vary. That's the big important thing, because it's samples. Samples vary, so the data varies, so the statistics vary. Alright, now I roll 5 times, alright, and I'm computing the proportion of those 5 that are odd. Because I rolled 5, the only things that are possible are 0 out of 5, 1 out of 5, 2 out of 5, 3 out of 5, 4 out of 5, and then 5 out of 5. So 0.5 is not possible here, but because the closest two things to 0.5 are 0.4 and 0.6, they're the most frequently occurring when we're taking, again, 10,000, we're doing 10,000 trials. And in those 10,000 trials, the most frequent things that occur are 2 out of 5 and 3 out of 5, the two closest things to that 2.5. Again, 0.5 is right there in the middle of these two, and this thing peaking around that 0.5. So what are we seeing here? We're seeing another approximately normal shape with the bell or the curve peaking at the population value, the expected population value. So in this case, again, it's weird to see this notation, but it's the mean, because it is a population. These are all the possible outputs that I could get of a sample size 5. It's the mean of the sample proportions is equal to, just use P to represent the population proportion. Mean of the sample proportions is equal to the mean, or the population proportion. Right, this is P in this case. Right, and remember, because it's a bell shape, the bell curve peaks at the mean. Right, because the mean is the mode when you're dealing with a bell curve. So that population proportion is the mean of the sample proportions. That's what this is saying. Alright, now let's again try to wrap our hand around the last thing, sample variances. So this is the same data set we've been using the last 2 times. I'm going to put both in my calculator. Alright, so there's the first data set, there's the second data set. I'm going to hit stat, one variable stats, and I have data in 2 lists. You don't have to tell it list 1 for list 1, but I am just going to put it in there to remind you. Okay, so there is the mean of that first list, there is the sample. Remember, this is a sample, so we're going to use the sample standard deviation. Okay, and to get variance, remember variance is different than standard deviation. You got to square the standard deviation. So I'm going to go underneath vars. As soon as you run one variable stats, you can do this. Hit vars, scroll down to statistics, find the sample standard deviation symbol, and then square it, and you've got your variance. Okay, so our variance here is 2.2. Okay, that's S squared. Remember, S is your symbol for variance. Okay, and then for the other one, I need to do the same thing I just did. Let me clear this out. I need to do the same thing I just did, except I'm going to tell it list 2 instead of list 1. Because my other data set, this data set, was stored in list 2. Okay, so now there is the standard deviation of the other data set. Alright, I'm going to go back and tell it to square the standard deviation. Alright, and I get 5.5. Alright, and just remember, variance and standard deviation are both a measure of spread in your data. Okay, this data set goes from 1 all the way up to 5, so it has a range of 4, but a lot of the values are centered there around 3. There's a couple 3s, a couple 4s. This data set has a range of 5, right, and then there's 2 that are really small, 2 that are pretty big, right, and then a third one that's really big, so or relatively big. So this one has more values in around the middle of the data. This has small values and large values, so there's more spread in this data set. So that's what, again, that's what variance tells us. All right, and then just like everything, like the other things we've been saying, the population variance was 1.707 here. Okay, these variances that we're seeing here, 2.2, 5.5 were bigger than that value that we were seeing before. So again, it's a sampling distribution. It's all the different possible variances we could get from sampling 5 things at a time. All those different possible samples we can get of 5 things at a time is what we're computing here, what we're trying to calculate. Now, it's a little different for variation and for variance. Notice this is not perfectly bell-shaped like the other ones. This is after 10,000 trials, and we don't have a perfect bell curve. We have this extra tail out to the right that we didn't have with the others. The others, you notice, they were virtually perfect bell curves after 10,000 trials. Right? But this variance, the distribution of the sample variances is skewed. We have a right skewed distribution. Okay, our population variance was again 1.707, 1.708 roughly. And if you look, there's 1.5, there's 3, 1.7 is roughly right around in here. Okay, so it's the skewness is it's not centered around the mean like we've been seeing with the bell-shaped distribution. Okay, so the distribution of sample variance and then also sample standard deviation, since it's the square root of variance, is not bell-shaped. It's got a right skewed distribution. Alright, now let's do this. Is one of the types of problems that you have to do in your homework. So this is the 4 wealthiest people. This is just an activity to kind of give you the idea of understanding what a sampling distribution is. These are the 4 wealthiest people in the world. Okay, this is in the country. Alright, so this is like Bill Gates and some of the other Microsoft and .com people. Assume that samples of size 2. We're going to take 2 of these at a time, are randomly selected from the population. Right. So we're going to take 2 of these values at a time. Alright, I'm going to copy them onto the next screen. Alright, so we're going to take 2 of these at a time. So I could take 45 and 45. I could take 45, 35. I could take 45 and 22. I could take 45 and 18. Alright, now I'm going to do this for every single possible combination that can result. Alright, so there's all the possible samples of size 2. And notice all I did is just list the last numbers, 45, 35, 22, 18, as the second number, right, all the way down. And then I just changed what number goes in front, from 45 to 35 to 22 to 18. Alright, that's the easiest way to come up with these. Now, the easy means to figure out, the sample means, alright, I'm going to write in red underneath here. The easy ones are the ones on the diagonal, because if you average 2 numbers that are identical, that the average is going to be that same number. So that's the easy ones to compute. Oops. And then I'm going to go through and compute the means for all the others with my calculator. Alright, so there's all my sample means. Now what you need to understand is this is every single possible sample mean that we can get, taken 2 at a time from those 4 numbers up there at the top of your screen. And this is it. This is all the ones that we can get. Now, what we're asked to do is go back and complete this probability table. So 45, right, it occurred 1 time out of the 16. Alright, so 1/16. Alright, 40 occurred 2 times out of the 16. 2/16 is an 1/8. And then basically what you see is anything that's on the main diagonal occurred 1 out of 16 times, and anything that's not on the main diagonal occurred 2 out of 16 times, or an 1/8. So that's what I did to fill in the rest of the table. Okay, you can pause it and look back and verify if you'd like. Now what I'm going to do is I'm going to put this probability distribution, this in list 1, right, both what's in black in list 1, and then what's in red in list 2, right, and this 0.125 is an 1/8, 0.0625 is a 16th. And then I'm going to hit stat, go over to calculate one var stats, and I'm going to tell it list 1, comma, list 2, enter. Right, our mean there is 30. Okay, I also want you to see that if I do 45 plus 35 plus 22 plus 18 and then divide that by 4, I get 30. That's the mean of these numbers. That's the mean of this distribution. But also, if I take all these sample means, all the values in red, put them in, I put them into the third list of the calculator, alright, and now do stat on var stats, but tell it list 3, I've got that data in the third list. I also get a mean of 30. Okay, so I'm getting a mean of 30 all the way across the board. So this goes back to what I was saying before. It's just further illustrating this idea. The mean of the sample means is equal to the population mean. Right? We found the mean of these 4 numbers to be 30. That's the population mean. And then these are all the possible sample means. And we found their mean to be 30. So that means the mean of the sample means, all of these numbers down here, was equal to 30. Alright, so the mean of the population is equal to the mean of the sample means. Alright, that's what we mean by that. Alright, last thing I want to show you, in list 4 I've created just the data set again. There's 4 numbers. I'm going to press stat, calc, one var stats, and I'm going to tell it list 4. Alright, and I'm treating that as a population. So I'm going to pull off that population standard deviation at 10.7. Alright, now I'm going to go into VARs, VARS. I'm going to come down here and I'm going to tell my calculator to go to statistics. And here's that standard deviation. And I'm going to tell it to store that for right now. Store that as A. Okay, so A on my calculator is now that number. Okay, now I'm going to do it one more time. Again, I've got in list 3 is all of those possible sample means. Right, so I'm going to go in there once again and I'm going to tell it to run that one variable stats. We've already done it on list 3 before, but I want to show you something real quick. Alright, there's the standard deviation of the sample means. So now I'm going to go back into vars and I'm going to tell it to store that standard deviation as B. Store B. Alright, now let me clear this screen out so you can see the two. Alright, A, this is the population standard deviation. This is the deviation of the means. Right, they're not equal. Alright, well, how far are they apart? How far off are they? Well, let's take A and divide by B. We get that number. Now, some of you may recognize that number, some of you may not. So pause it, think about it for a second if you want to, because I'm getting ready to show you that number is roughly the square root of 2. Right, exactly, because the calculator computed it so many place values. But we're getting the square root of 2, where our standard deviation of the population has been divided by the square root of 2 to get us to the standard deviation of the sample. So what does that mean? What does that translate to what we're going to be doing? The standard deviation of the sample means is not equal to the standard deviation of the population. It's equal to the standard deviation of the population divided by the square root of the sample size. Alright, this is a very big idea. For not just the rest of chapter 6, but for chapter 7 and chapter 8 as well.